A little bit of an addition to what we know about finding maximums and minimums and analyzing functions using calculus. We're going to be looking in section 5.4. What we're adding here is finding maximums and minimums on closed intervals. So here's a fact. If f of x, some function, is continuous, doesn't have to be differentiable. In other words, doesn't have to have it doesn't have to be smooth. It could have sharp corners. That would be fine. This would still be true. If f of x is continuous on some closed interval from a to b, then there is an absolute maximum and minimum value of f of x on that interval from a to b. So let's just what's the big deal here? Isn't that generally true? Is it generally true? Well, first of all, there's lots of functions. For example, let's say f of x is equal to x squared on the interval of all real numbers. Then there's an absolute minimum, sure, but there's no absolute maximum because it just keeps going up forever in those directions. So I think that helps us understand what's up with the this closed interval thing. If you cut it off, then it is going to dead end into those, and it forces there to be an absolute maximum and minimum. But it does have to be continuous all the way from A to B. For example, let's say this is f of x is equal to 1 over x minus 1. Looks like this. On the closed interval from 0 to 2. Well, there's that point. That'd be at 0, 1. Sorry about that. It's not drawn to scale exactly here. And this would be the point 2. Sorry, that's 0, negative 1. And this is 2, comma 1. So is there an absolute maximum or minimum here? No, because this plunges down forever. So there's no absolute minimum, and this plunges up. Plunges up? I don't think that's right. It's the opposite of plunges. Plunges. It ascends, but that doesn't have the same sort of time sense of plunge. Seems like a plunge is happening pretty fast, and ascending doesn't really have a time thing. Anyway, you can think about that. Let me know. Anyway, this goes up forever, and there's no absolute maximum. So that just gives you kind of an idea why this has to be true, why it's only true if you have, or it's only guaranteed to be true, I should say, if f of x is continuous on that closed interval. And here's the deal. There's nothing difficult about this. You just need to know to find the absolute max and minimum of f of x on the closed interval from a to b. Do the usual analysis, which means I set f prime of x equal to 0, and then you could do the first or the second derivative tests to see whether you got maximums or minimums in there. And then check the endpoints. And we're adding a new thing here. So what's the number one mistake that new calculus students make when they're doing this, finding maximums, minimums on closed intervals? The number one mistake that they make is they forget to check the endpoints. Because they know how to do this other, like the regular analysis stuff that we were doing in 5.1 and 5.2. But you got to check the endpoints if it's on a closed interval. Why? Because I don't think it's going to be very hard. Maybe you already understand why. Maybe you got an idea about this. So let's say we got a function here, but let's say the closed interval we're looking at is from here to here. So if you do the regular analysis, the usual analysis stuff, what that is going to turn up for you, it's going to show that there's a max here. Maybe you use the first derivative test and you see that the derivative is going from positive to negative. And you're like, oh, so that's a maximum. Yep, you're right. And this is a minimum. But if we're looking for the absolute maximum, that means the very highest value, absolute minimum, the very lowest value that the function attains on that interval. And so this here, as it goes up here, this endpoint is actually a maximum. Is it the absolute maximum? No, not in this case, because this looks like it's a little higher, right? So, but we do have to check that because it's a candidate. It is a maximum at that endpoint. And it could have been the absolute max. Here, this minimum, is that the absolute minimum? No, the absolute minimum is at the endpoint. That's good. I think visual, why that's true. If you just go chopping a function off there, well, you could have chopped it off when it was plunging down to negative infinity or something, so you could get something lower than any place where the derivative turned out to be 0. And then the last thing to say about this is you need to make sure you are answering the right question. This is another common mistake. So what are the two questions you could be asked? Where does f of x have a max or minimum? Probably absolute in the context of this section. The answer to the question where is an x value. Right? Where is like, what's the x value where it happens? But now, in this section, for these absolute maximums and minimums, we will often be asked, what is the probably absolute, it's going to say, but in general, we could say, what is the max or minimum value of the function? And that, the answer is an f of x, or in other words, a y value. So just pay attention to the where and the what. If you want to just be super safe, cover your bases all the time, you can always say the maximum, scribble on the other side of this real quick. You want to be safe? Always say that, so let's say you did your analysis, you got your value, and let's say it happens at some value, let's call it C. The max, let's say this particular one was a maximum, value of f is, and then say f of c is equal to whatever the number is. So here, like, you're including both of those answers. Here you're going to put your x value, and here you're going to put your y value, and that includes both of them as part of the answer. So then you're safe, right? Whichever one was asked for, you got them both. And that's all we're adding to this. That was easy.